for introduction. I'm Tomoharu Ugawa of the University of Tokyo. I'm talking about the profile guideline for optimization of hidden class graph, JavaScript VM in embedded systems. Sorry for the very long title. This work is done with Stefan Mao and Richard Jones of the University of Kent. These days, JavaScript engines for IoT becomes popular, and several JavaScript engines for IoT are developed. For example, IoT.js, Modable, and other JavaScript VM, EJS VM. One of the challenges for these JavaScript engines for IoT is the memory footprint. Typically, the microcontroller for IoT has around 256 kilobytes of RAM. For example, this STM32 microcontroller has 256 kilobytes of SRAM, and Raspberry Pi Pico has 264 kilobytes of SRAM. But in our measurement, our EJS VM uses more than 20 kilobytes of RAM for meta objects, and this number 20 kilobytes of RAM is the lower bound, and for some programs we observed that meta object uses more than 60 kilobytes of RAM, which is more than 20% of the available RAM. This work is to the goal of this work is to reduce this area. In this research, we assume that the program is fixed for a particular IoT product. For example, for product A, the virtual machine only executes this AJS. And for product B, this virtual machine always executes this BJS. In this situation, it is feasible that we optimize the virtual machine for this particular application. This is the overview of work. This work applied this specialization idea to the hidden class graph. Roughly speaking, hidden class graph represents the type information of objects. Hidden class graph is created and grows during execution in accordance with the program behavior. But in this research, we generate the hidden class graph offline statically. First, we collect the behavior of the object in the profiling run. And then we construct the hidden class graph statically and optimize it. In the actual runs, we use this optimized static hidden class graph. Before we explain our proposal, let me remind you about hidden classes. Because JavaScript is dynamically typed language, an object in JavaScript does not have static type. So the properties of the object are added dynamically, and the set of properties depends on the control flow. For example, this function creates a location object here and add properties from the value obtained from the GPS. So first it adds a longitude property, and then it adds a latitude property. And the object created without any property here, and then it obtains the longitude property and then latitude property. And then this program adds the altitude property conditionally. So for some object, it obtained the altitude property, but for the others, it doesn't. If the caller of this function doesn't add any other property, all the object created here has one of these four layout. Our JavaScript VM EJS does not does not store objects in this table-like structure, but we use hidden class. Hidden class is a kind of meta object that has the object layout. So this is similar to the class object in Java. With this is the hidden class. For example, this object has three properties whose index are 0, 1, and 2. The object with hidden class is represented by the pair of the hidden class and the property array, which are the actual value of the property. So for this index, the value for the longitude is stored. And this hidden class is shared with multiple objects that have the same shape. So the hidden class is immutable. When we add a new property to an object, it does not. The VM does not modify the hidden class, but it finds a next hidden class, and if it is not created, it creates a new one. In this hidden class transition, by this hidden class transition, the property array should be reallocated because we cannot extend it, this array because there may be another object. To find the next hidden class quickly, the virtual machine maintain the created hidden class in a tree-like structure called hidden class graph. In this structure, the node is hidden classes, and the edges are transition labeled with the property name. So if a longitude property is added in this property, the hidden class changes to this one. And if latitude property is added to the object in this state, it changes to this state. When the new property is added, for example, the location, if we add a timestamp to the location object, it creates a new the VM creates a new hidden class, and it adds to the existing hidden class. If we remember that the altitude property is added conditionally, some objects are returned with this shape. So for these objects, if we add a timestamp here, a new hidden class this hidden class is created, and this is added to this state. So now we have a branch in this hidden class tree. Okay. So next, I explain our proposals. This is a detailed overview of our work. So first, we collect the final state of the hidden class graph from the profiling run. And then we optimize this hidden class graph with this policy. The policy is that we reduce memory footprint by shrinking the hidden class graph and by reducing the size of each object. But we allow some space inefficiency for speed. In the actual runs, we use this optimized hidden class graph, and because this hidden class graph is stable, the production VM can be applied runtime optimization relying on assumption that the hidden class graph is stable. In this work, we tried these two optimizations. For the first one, we observed that 95.8% of allocation sites are layout monomorphic in our benchmark program. The layout monomorphic allocation site is allocation site where all objects allocated there obtain the same set of properties in the same order. So, for example, this program, in this time, the altitude property is added unconditionally. In this program, all objects created here obtains this property in this order. So this is layout monomorphic allocation site. For the layout monomorphic allocation site, the object eventually has the same hidden class. For this layout monomorphic allocation site, we can apply pre-transitioning. So we eliminate all hidden classes, but the last from the hidden class graph. So if we use this single node hidden class graph, all objects allocated here have the final layout in the first place. So no re-allocation overhead of the property array is applied. One thing we have to care about is that the initial property, we have to initialize the property array slot with a special value empty to indicate that the property is absent. This is necessary to keep the semantics of the JavaScript. Our first optimization, elimination of intermediate hidden classes, is a generalization of the pre-transitioning. The pre-transitioning eliminates all nodes but the last one. And this elimination of intermediate hidden classes eliminates all internal nodes but branching nodes. So for this hidden class graph, we eliminate these hidden classes, and then we get this hidden class graph. This hidden class graph. However, aggressive elimination of hidden classes, aggressive elimination of internal hidden classes may increase memory footprint because the memory for all possible properties are reserved when the object is created. So if a part of object get extra, if only a part of object get extra properties, or if properties are added in the future, sub area are reserved without using. For example, for this program, if this has altitude is likely to be false, then most object has this area for altitude property with empty. So these slots are wasted. So we modify the optimization. We propose popular hidden classes. Here we define the popular hidden class as a hidden class that has many instances. For this example, this object is popular because most object does not have altitude property. In this case, we preserve this hidden class. Then the objects are created in this state. So objects are created with two slots, and if an object and few objects that get this altitude property transition to this state. More precisely, we define the popular hidden class with this expression. The popular hidden class is a hidden class that has more than k instances. In our case, the k we set k is k10. Because the number of instances varies during the execution, we pick the maximum number of the instance in the entire execution. But we actually we sample the number of instances at each garbage collection in the profiling run. Next, we go on to the second optimization. This is a motivating example for the second optimization. In this program, the location object gets longitude and latitude property, and it gets altitude property conditionally, and then it obtains time property unconditionally. In this case, this object eventually has this time property, but because this there is a conditional branch, the hidden class has a branch. The problem is that even for the popular hidden class, the object experiences transition. The object is created in this state, and it transitions to this state. So the transition involves the reallocation of the property array. Our second optimization moves this unlikely branch to the end of the popular branch. So we move this branch to here. The time property appears here has already been added in this transition. So we do not add the time property again. As a result, the order of the property may change from the from before moving to the after moving. But this order works. And as a result, we have a linear hidden class graph. And after the optimization one, we have this hidden class graph. Without moving branches, we have this three node hidden class graph, and the popular popular object with popular hidden class experience hidden class transition. But after moving branches, the object with popular hidden class does not experience the transition. And we found that the moving branch is also benefit to inline caches. Inline caches is a cache of the results of the index lookup. Yeah, it is the cache. Inline cache is a cache of the index lookup. So this is the implementation of the inline cache. If the incoming object has the hidden class, has the same hidden class as the cached one, it gives this cached index. But if the hidden class does not match the cached one, it invokes the throw path to look up the index from the hidden class. So if we move the branch, the variation of the hidden class in the hidden class graph reduced. So the chance of the inline cache hit improves. Next, we go. I explain the runtime optimization relying on the assumption that hidden class graph is stable. We have a plan to plan for the runtime optimization for these two items. One is in-object allocation, which I explain in the next page, and the other is baking hidden class graph into flash memory. But the second item has not been implemented yet. The in-object allocation is that we allocate all properties in the object rather than in the object like this, rather than using an external property array. And this in-object allocation eliminates this indirection pointer, so we can save this area. If an extra property is added and the in-object property area overflows, we convert this last property area for the indirect pointer. We implemented this in EJS VM and measured the performance using the ReFastYet benchmarks and two variants of the programs in the benchmarks. The first result is about the size of hidden class related data. The hidden class related data was reduced by 91.3% 61.9% on average. And the maximum volume of all objects, including the hidden class related data, was reduced by 17%. Regarding to the execution time, the normalized no program got slower by optimization, and some programs got faster by around 20%. One of the reasons is that the elapsed time by GC becomes shorter because we eliminated reallocation of the hidden class array. Reallocation of the property array. Another reason why the execution got faster is the inline cache miss ratio. These programs, for these programs, the inline cache miss ratio was reduced, and this contributes to the execution time. In conclusion, we proposed offline optimization of hidden class graph, and where we moved in unlikely branches, and we eliminate intermediate hidden classes while preserving popular hidden classes. As a result, we reduced hidden class related data by 61.9% and footprint by 17%. We've observed that no program got slower, and we moving branches improved inline cache hit ratio. Last of all, let me introduce a workshop held in Tokyo next year. We have more VMs workshop in Tokyo. This workshop is co-located with the programming conference, where the submission deadline is in January, so you have plenty of time to prepare the submission. Thank you very much.
Any questions?
Do you have different hidden classes for different JavaScript functions? Like, do you have is a prototype field separate from the hidden class?
Sorry?
Do you have, so VA puts the prototype into the hidden class for JavaScript objects. Do you do the same in your VM?
Same what? What is?
So in in V8, basically the JavaScript function from which an object was created as part of the hidden class. Do you use a similar technique in your VM?
Sorry, I don't understand what technique the V8 uses.
Okay, we can talk about one.
Okay, thank you.
Any other questions? I'll ask one. So, oh, Jeremy.
Hello. Do you feel that the "Are we fast yet" benchmarks are representative IoT workloads?
Good question.
I'm sorry, and if not, what else could you use?
I think some of the we fast yet benchmark represent some aspect of the embedded programs, For example, the JSON parser, it has a JSON parser. So, for example, the IoT device may receive request in a JSON format using HTTP. So it may represent some aspect of the IoT programs.
And any other questions? I'll save mine for afterwards. I'll talk to Tomoharu directly. Okay, thank you, Tomoharu.